everyone. Welcome to the Alerts in the Crowded Fields session. I'm just going to start off with some of the reminders that you should all be pretty familiar with at this point. We have a code of conduct, and if you witness a violation of the code of conduct, please contact one of the contacts listed there. We do have Zoom, and especially in this room, please use the microphones if you have a question to ask, and we will be monitoring the Zoom and Slack chat if there are any questions. The way that the session is generally that we've organized the session is that we have some of the talks on alerts, then some of the talks on crowded field science a little more generally, and then we have a lot of time for discussion. And so if there ends up being a lot of discussion that's sparked by the talks, it does not necessarily need to be saved to the end. We'll just make sure that everyone has been allocated their time. But yeah, looking forward to a productive session. So first, starting up will be Ian Sullivan.
All right, thank you very much for inviting me. I'm going to give an update very briefly on the alerts that we have issued so far in the crowded fields, and then focus on two pipe issues that we have worked on over the last year or two that most affect crowded fields, and just dig into those. So first of all, copying a slide from the Science Pipelines talk that you may have seen just a moment ago from Yusra. This is the visits that we have taken so far in approximate depth, just to give an overview of what we had in DP2. But more specifically, I wanted to focus on what we have sent as alerts. So here is a heat map of the source density of DIA objects that we have in our working PPDB for right now. So where the record of what we have in objects made from alerts. You'll notice that we are unfortunately missing alerts through the galactic plane. We don't really have a lot of alerts currently in very crowded fields because we have not deployed the templates in the galactic plane region. And if we actually focus that on DIA objects that only have 3 or more DIA sources, that shrinks further and is really focused on our deep drilling fields and a few calibration fields that were used in calibration. And similarly, to show what we have taken so far with DIA sources, again, we can see that those clouds, again, missing a lot of the galactic plane here and focusing on mostly these different deep drilling fields, and focusing a little bit further, only show the high reliability DIA sources. That doesn't actually shrink quite as much. And that's about what we have so far. Hopefully we'll be able to deploy new templates soon, and then we would be able to get you more alerts in more crowded regions. So in order to get those alerts in more crowded regions, we've been working on a couple different pipeline changes to process that data better. And first I would like to tell you, and I just copying over again a slide from the Science Pipelines talk to give you an estimate of the completeness that we have in a couple of different fields, the Cosmos field, which is fairly sparse, and the M49 field, which is a bit more crowded, and I'll talk a little bit more about that later, where we are getting a pretty good recovery of our positions in those fields with our fake sources. But what I really wanted to talk about are the two different pipeline changes. The first one I'm going to tell you about here, this work is all attributed to Lauren MacArthur, who is not here in person, but she has done great work in making it so that the crowded fields pass calibration, and we're able to get to the point of making measurements, making coads in these regions. That work is on adaptive thresholds in calibration. So originally we had been thinking of, for prompt processing, needing to switch to an alternate pipeline configuration in crowded fields. This has some disadvantages because then there is a step change in what configuration is used in different areas. But Lauren worked on something much better, which is to have the pipeline itself iterate and choose the detection threshold and scale that until it is high enough and do iterative background subtraction with that as well, so that all of the sources that you're going to use for calibration are now isolated. And we can then do our PSF measurements, our object matching with the reference catalogs on these isolated sources. And it works very well. It's in the pipeline, and we don't have to have an alternate pipeline for crowded fields. The same one can run, and it will just scale within each field. All of this is within calibration. So then we have made the other separation in prompt processing between the catalog that is used for calibration and the catalog that you might use for science. So that is the direct source catalog that is now produced in the daytime pipeline and will be made available shortly, I think this fall, where we'll have the 5 sigma direct source catalog that is produced not in prompt because we don't have time for it. Prompt is just doing the calibration. It will scale, it will throw out whatever sources it needs to run fast. And then in the daytime, you get a nice deep catalog, even in the crowded fields. I should point out one difference I highlight here between alert production and the data releases is that we tune this even further to run faster. So we do not include all of the iterative steps. And so it is not going to get to quite the same level of refinement in alert production, but we also, every second counts. So an example of how this is performing, I'm showing here from Lauren an image from the Trifid Nebula of the state before her adaptive thresholds. And you can see here the blue masks that you see everywhere are detected regions. And in green are the sources that are remaining for PSF fitting and calibration. And they're all clustered around this high extinction region, and it's not across the entire image. So there's just very few stars, and they are biased to one region. And if you didn't get that extinction region, you wouldn't have any stars. Turning on adaptive thresholds, the color changes dramatically. It's still the same color scale. So the detected region shrink tremendously. We now have isolated stars because we're only detecting at a much higher threshold across the image. We have stars that are scattered across the whole image. We can do calibration that runs well. As another example, here's another region just a couple of degrees away. In this region, our reference catalog has 670,000 sources per square degree. We don't find a single isolated star in that region suitable for calibration. So everything fails. With the adaptive threshold, all of a sudden, everything is reasonably isolated, and we're able to recover that. On a larger scale, because here I was just highlighting these 2 images that were representative of it, Lauren studied this over 287,000 images taken in this approximate region, give the RA index there. And in that overall region, prior to these changes, almost half of the images failed calibration. With these changes, we're now down to 1.6%. And of that 1.6%, we can attribute most of those failures to specific issues that is including bad image quality, where we wouldn't be able to calibrate it because we have donuts. It is including regions where we are failing to match to the reference catalog because our reference catalog in that band does not have sources that are suitable for us to calibrate. And so I would like to thank Lauren for this tremendous improvement in our calibration performance in crowded fields, as it is working quite well. And it does not require any custom settings or pipelines. It just will adapt and run in all of the regions. Then the other topic that I wanted to highlight is a new topic. We typically have stated that even in crowded fields, the difference images are still sparse enough that the dia sources are measured independently. But in the crowded field, we do actually then lose some sources. And this was highlighted to me also from the solar system group that they were losing a few percent of known solar system objects because the object landed close to a masked plane or on top of another artifact. And so they were losing these sources due to blending. So what I'm showing here is a prototype, but it is close to completion. And I expect it to be in production and in the alert stream by the time that we are back on Sky. Shown on the left here is what we have in the stack. And just highlighting, all of this is one footprint, which is all one contiguous region of detected or detected negative pixels. And so these two objects, the subtraction artifact and this variable star that here is negative because it was brighter in the template, are merged into one, and the detection is centered here. This is lost. With the simple deblending, the subtraction artifact, which includes multiple complex peaks, is retained as one artifact, rejected, and we now have split off the negative source, which is detected at, there it shows the reliability score of 1.0. It's a high reliability source. It will make it into the measurement. I wanted, yes, I highlight where those points are. I wanted to tell this group a bit about those details because I figured the crowded field group might care about the implementation. And since it's still a prototype, I really would welcome feedback on additional components that I may not have taken into account yet. So first off, why is this a custom deblender? And the main thing is that typically a deblending problem can't handle negative sources very well. And with the dia sources, we must do that. And we also really need to maintain subtraction artifacts as one artifact and not a whole plethora of artifacts. And dipoles really are one dipole and not two different sources. So I wanted something that ran very fast. This prototype on our typical images runs in about a second or less. And it's just a simple Gaussian mixture model of the peaks. So it runs between detection and measurement so that we can attribute the pixels within each footprint to the different detected peaks and then assign those pixels to one and only one dia source. So this does have implications on measurements on those dia sources because the other dia sources during measurement, their footprints are all set filled with noise instead. So it is possible for two that are close together and the contamination between the two is low enough that we still make the measurement, it will be missing some flux because it has been assigned to the other dia source. And I don't know of a good way around that, but I am open and listening for suggestions on improvements of how we can better allocate this flux. I have long details here. I'm not going to go through all of them. I invite you to take a look at the slides for details and come and talk with me afterwards. I wanted to now give you just a couple quick examples before, while I wrap up to keep to time. I wanted to highlight an example with the changes in completeness. The completeness plot that I was showing before was including the deblending. Without it, in the M49 field, our test shows 96% completeness. Including the deblending, that completeness bumps up to 98%. So it is noticeable. It's not a huge factor, but it is a noticeable improvement. Now for some examples. Here is a typical type of case that we would lose before. You'll note that on the left, there's no sources marked there at all. That's because these two sources, dia sources, were blended with a diffraction spike, which was the dominant source and lost. With the deep blending, they are separated out, and now we can recover and measure dia sources that are adjacent to an artifact like this. A couple other quick examples, some more complicated fields where we have some mixtures of dipoles and subtraction and artifacts and another negative source. Again, it separates them out, it carves these out into their independent regions and tries to maintain these clusters of subtraction artifacts as one unit so that we, again, don't receive a bunch of junk sources. And I think I'll leave you with one last one. I'll point out this is an image of that was a very bad subtraction, and I picked it out because everything was subtracted badly, and so this was showing a more crowded case. That is why the difference image here shows so many peaks, is that it was a bad subtraction overall. But it still runs there and carves out, you can see in the image, the outlines of the different sources and what it is able to separate and what it is not. These are a little bit too close, and at least the trade-offs I've been making so far leave close sources like that undeblended because they're just too much like the subtraction artifacts that I'm trying to suppress. And I think that's where I wanted to leave it here. Thank you all, and take some quick questions. Run a mic.
How close is too close?
Good question. What I'm working with right now is 2 PSF full width half maxes of each other. Everything within that gets clustered together. And if they are bright objects a bit further apart, with the Gaussian mixture model surpasses particular thresholds, saying that the one source really is subdominant to another within its own footprint, then it just gets subsumed into that as well. So 2 PSF full with half maxes or greater if one of the objects is very bright.
Exactly. And I was thinking that whether this could be affecting somehow transients next to a galaxy. We see galaxies that are not well subtracted. It would be perhaps good to look at those while this is happening. So,
yes, I mean, that is exactly the case that this is, that I was designing this for, was this, a transient next to a subtraction artifact. I wasn't working with examples of supernova. The training set I was working with was from Jake, and so it's mostly asteroids on top of other artifacts. Please do. Yes, Eric. Oh, you can run. Oh, sorry, there's a microphone over here.
I was just going to ask about, do you have an intuition for what would happen with transient nebulosity, like from light echoes? And
I hope that they would all be, that would remain clustered together. If we detected it as a source at all, and it's not clear that we would detect it. I think if we detected it, it would then get rejected later. The example that I've looked at was a comet trail, and where the comet core was detected beautifully as a nice dia source, and you could see visibly the comet trail in the image, which made it in, set the detected region, but did not become a dia source that would pass any of our cuts. And so it is possible that in that case would suffer the same fate. And getting real diffuse transients to pass, I really need some good examples of that, because there's very little that is, diffuse that is a real transient.
I was just going to make the point that you very well know that we have good code for injecting fake sources onto hosted galaxies, and we can assess the effect of completeness systematically.
Yes, in fact, the completeness plot that I was showing included all of the injection on top of hosted and hostless sources. So some of it was specifically injected on top of galaxies for that, and included images with bad subtractions as well as good subtractions.
I think similar following up to the Galaxy stuff. In the Galaxy session, Dan was just showing us their spike tool, where they did a new subtraction. And when I saw the spike as a result, and therefore that object being missed, is there any cross collaboration between you guys doing this with the difference images and those guys doing it with the actual subtraction? Are they same tool, different tool, completely different?
Completely different. So with the spike, so this is subtracting the model of the spike instead of doing the spike masking.
Yeah.
Yes.
That kind.
Right. No. Sorry. I wrote the spike masking, and that is in general solves some problems but creates others, as they were analyzing there, and that is complementary. But I have not worked with Dan on that. No.
Separate. Okay.
Yeah.
Thanks.
I can read it out.
We have a question on Zoom from Markus Hundertmark. Could you please explain how the images are resampled before subtraction? The dipole image appeared to show image distortion-induced structures, which resampling, or rather image alignment should address.
I'm not quite sure I fully understand the question, but I'll leave up what I believe was the relevant slide with the dipoles. So, no, these are the science image is not warped at any or resampled at any point in this process. The coads, are constructed originally from other science images and would be have a simple warp with a Langtos 3 kernel, which then to the tracks and patches that then is warped back to match the science image and subtracted. The noise of those templates is typically much lower than the science image. So a lot of what you are seeing here is dominated by the science image and therefore does not include any resampling or warping. But I can take that to Slack and continue the conversation there.
That's exactly the
Okay, great.
Thanks. Maybe I'll ask one last quick question as chair. With regard to the 5 Sigma source catalog that be available during the day, would that be available through the prompt product database or by some other means?
The prompt product database is only going to be of the DIA sources and DIA objects, the DIA4 sources and solar system objects, so all from the difference image side. The prompt catalog will be made available, Eric, through the butler? Yeah, just through the butler as a catalog that you can retrieve through the RSP.
Thanks.
All right, thank you all.
We can continue the conversation. But let's give one more round of applause.
Oh, you need the thing, otherwise. Oh, okay, sorry about that. There you go.
Hello, my name is Natasha Abrams. I'm a finishing grad student at UC Berkeley, and I'll be talking about discovering and interpreting microlensing events with Rubin alerts via Antarix. So first, let me explain what gravitational microlensing is. There's a couple of talks this session about microlensing. Gravitational lensing in general is when you have a massive object that's going to bend light from objects behind it in its line of sight, creating distorted images of that distant object. In the case of microlensing, instead of like a big galaxy doing the lensing, we're talking about individual stars and black holes that are doing the lensing. So you would have some distant background source star, which is represented here in red. And here we're in the frame of the lens, which could be some star, it could be a black hole, it could be a planet. And as they pass by one another, you get distorted images of that distant source, which are represented in blue. In the case of microlensing, you generally can't actually resolve those distorted images. And so instead, you see an increase and a decrease in brightness as they're blended together and as the source and lens pass by one another. There are a couple of measurable quantities in microlensing. One is the Einstein crossing time, or TE, which you can think of like the duration of the microlensing event. This scales with the square root of the mass of the lens, with the relative parallax between the lens and source, and inversely with the relative proper motions between the lens and source. This can scale from on order of hours to exoplanets to 100 plus days for black holes. There's also the microlensing parallax, which over the course of the year, as the Earth goes around the sun, you can see bumps and wiggles and asymmetries in the light curve that are caused by looking at the microlensing event from different angles. So in the plot below, you can see in red, there's a light curve with very little microlensing parallax, which is very symmetric. And in purple, there's one with a lot of microlensing parallax, which is more asymmetric. This scales inversely with the square root of the mass of the lens and with the relative parallax between the lens and source. So here's a set of simulated microlensing events where we plotted microlensing parallax versus Einstein crossing time. And you can see in red are simulated black holes. And they start to separate out in that part of parameter space. And so with photometry alone, you can start to identify them in this space. However, there's still a lot of dispersion due to degeneracies between the masses, parallaxes, and relative proper motions. And this plot doesn't even include the error bars, which would be very large for most parallax cases. But beyond black holes, microlensing actually has very broad applications throughout the galaxy. You can look for things like mass functions of stars and black holes. You can measure them with by other means than a lot of the other traditional methods. You can look for binaries. Here they jointly fit the initial mass function slopes along with the binary fraction. And we're not able to constrain it, but in principle you could. You can also look at the galactic kinematics. Look at the bar angle, which microlensing is hugely sensitive to. Things like proper motion distributions and stellar densities. You can also look for unseen or hard to probe objects, like brown dwarfs of this, which is, this light curve is a brown dwarf binary pair. Exoplanets, low mass ratio binaries. You can put constraints on primordial black holes and look for stellar mass black holes. But what a lot of these unseen or hard to probe objects have in common is that with the Rubin data alone, it's going to be difficult to identify individual events or to look, and as you can see there, there can be a lot of fast features that the Rubin cadence wouldn't be fast enough to allow. And so that's why we care a lot about alerts, to either follow up these objects, to either follow them up with high cadence follow-up, or astrometrically, which can be used to break some of the degeneracies I mentioned earlier. And so the Rubin TDS microlensing subgroup has been working on a few different filters for Lurse, I think, and Antares. With Lurse, there's, we've been working with the team to include in their hierarchical machine learning classification a microlensing class, along with Think, using Microlia, which Daniel Godinez is leading. And for both of these, there's been a lot of simulation work in the group to be able to accurately simulate the Rubin mind curves so that the machine learning algorithms can be trained up correctly. And then for Antares, we're taking a little bit of a different approach where we do progressive filtering and fitting to be able to identify microlensing candidates. And the idea is that if we have all these different methods, then we can bring them together in the galactic science OPM, which Marcus Hintermark has developed, to be able to more confidently identify microlensing events and to follow them up, and also to add in additional metrics like weighting an object by the number of stars squared to try and eliminate extragalactic contaminants. So then we can follow up. To go into slightly more detail on the Antares filter that we've implemented, we start by eliminating light curves with too few points, eliminate the known variables or transients associated with a known galaxy, use the von Neumann parameter to eliminate light curves that are too uncorrelated, since microlensing is expected to be smooth, or too skewed light curves. We then do a least squared fit to a 4-parameter microlensing model and eliminate those that don't pass our chi-squared threshold, or those that have too correlated residuals after the fit. And then we save those fit parameters in the locus so they can be accessed later. So through Antares and through the Galactic Science OPM, we have some beta candidates that are available. They're of course best when they have a ZTF baseline and you can tell that they weren't variable in the past. You can see on top is one of our better candidates, so it's very difficult to tell if that's actually microlensing, especially with only the rise side and without being able to tell the baseline. And there's some that are definitely not as good, that appear to be associated with some sort of extended object, which we don't expect from microlensing. So our current challenges are that we want to include more robust microlensing fits once Antares upgrades their Python environment, to tune our thresholds for Rubin data as more comes in, to include to also tune the threshold for the star galaxy classifications, especially for the faint objects, where I know there's a lot of development that's currently being done to help improve that. Attempting to use color to help us classify events, since microlensing in the first order is achromatic, and we're looking forward to alerts in the galaxy. Thank you. Take any questions.
Thanks. Nice talk. For that one event that looks somewhat promising, do you have a lower limit on the time scale for it? Since it does seem to be rising fairly slowly.
Yeah. So I think that the way that you can think of the Einstein crossing time is kind of like the full width half max ish of the light curve. So I think that this one, it was like something like 60 to 100 days was the current fit, but that could evolve.
You thought at all about how you're going to handle, Rubin of course has 6 different filters and will offer to be coming to you thought about how you're going to put that in the filters?
Yeah, so well, I guess for the hopefully after at least the first year or so, the baseline should be fairly obvious for most microlensing events. For reference, the peak of the durations of microlensing events is between 20 or 30 days. For the part where it's actually varying, I've been doing some experimenting with looking at the cross correlation between the different colors. Since with a lot of other phenomena, even if the peak time might be dependent on the chromaticity, which is not expected for microlensing, so stuff like that.
I guess in the interest of time, we can move on to Slack with this conversation, and I think it's pretty good.
It's actually obvious. I think it's actually obvious.
Oh, sorry. I'm so sorry. Abby, you're next. Chair is
Thank you.
So I'm going to talk about an alternate method for doing photometry of stars in overcrowded regions, which is relevant to the general area of what we're discussing in this session. So I'll go straight to it. I'll try to keep the presentation short so that we may have some time for discussion at the end, but let's see how that goes. So this is, of course, as I said, of general interest for the LSST survey, and there's a crowded field task force that's working on other methods, one based on BAO code, which was discussed yesterday at one of the sessions here. And this is about an alternate one that uses a DUFO-based effort, whose attributes are it's faster and without loss of accuracy and completeness, and it's been widely tested in the relevant context for both ground and space-based imaging in very crowded fields, for finding Cepheids in external galaxies with HST, and for looking at the bulge and looking for variability in the bulge from DECAM data. So just a few words about what limits the veracity of stellar photometry in crowded fields. The problems you have to face are disentangling the profiles of nearby objects, and not just that, you can have chains of objects. One influences this, and then that is influenced by some other neighbor, and so on. That's what I mean by chains. And you have to fit the PSFs to measure the relative brightnesses of individual objects, which makes it necessary, really, to find the PSF as well as you can, because that influences the other relevant factors here, which is the accuracy of a photometry is going to be determined by how well you've found the background for each of the objects, how well you've disentangled neighbors, which is the deblending problem in LSST parlance, and determining the aperture corrections to calibrate the relative brightness to some sort of standard magnitude scale. All right. Even though we're interested only in stars, we still need to account for neighborly contributions from galaxies and other topologies. And remember, when you go deep, as in the co-added images, you're past 24th magnitude there eventually, and the background galaxies, their numbers go up. They don't look like stars, but you still have to account for them to get the background correct. Stellar fields can come with other background features, such as caused by extinction from intervening dust structures, and I think Ian showed examples of that in that field, so I won't dwell on it. So our sense was that the DP1 and DP2 pipelines leave room for improvement, and hence the crowded field task force, which is led by Massimo at the INF in Naples. I'll describe here an alternate pathway, and mostly I'll show you figures using the DuCode program by Schechter. He's not in the room, I don't think, but he's here at the meeting, to supply it with good PSFs and improved background estimates, so that it can run in batch mode, because we won't have time to be monitoring what's going on. So the two DP1 fields that had crowded field examples was one, the Fornax dwarf galaxy, which is on the left, and on the right, the globular cluster 47 Tuc, which has enough saturated stars in its middle that some of those images were not really made public. Okay, so we found one eye image in 47 Tuc that covered the central area, the eye band, and we'll talk about that when we go. So this is that field, which is the CCD that came on top of it, and this is a part of that field, and you can see the white outs are the places that were masked. On the left side, you see the image as it is with the bad things masked out, including charge trails on saturated stars that run in one direction. The core of the cluster is somewhere here, and even you have a whole ramp of stellar densities going out. This is the result of running the code on it with a good PSF. And you can see that certainly in the sparse regions, the subtractions are really smooth. And I'll show you more about the inner regions as we go. The round white blobs that are injected in the right-hand images are basically saturated stars that it found that we decided to flush out because we can't handle them. This is a region picked out from about that area. That's not showing. I mean, somewhere here. And you can see on the left the image as it appears, and on the right with all the stars subtracted. Now, not everything is perfect, but you know, most of the stars are clean. This is looking at a less than 1% slice of the dynamic range of the image, so right near the sky. So what we have fitted and subtracted from the stars that are near saturation is, you know, less than 1% of the star itself. So we're getting pretty close. This is the same thing, except on the right-hand image now contains the model image. So if you subtract the right panel from the left panel, that's what Ducode decided to fit. The big black spotches are really the white spotches that got turned around, but never mind those. And you can see that some places, like for example here, you know, it's pretty good about finding groups of stars, and you can go further into crowded regions as you go. But they won't find absolutely everything, but you sort of learn to live with it because that you're going to hit some level of crowding. And usually with average nearest neighbor distances that are of order of up to, that are larger, average nearest neighbor distance is larger than 10 pixels, we get very good results. After that, you start to lose things, but what can you do? This is a slightly different view, one of a sparser region and one on the right, a denser region up near the top, with M&Ms thrown in. The red dots are things that Ducode identifies as bona fide stars. The green dots are things where it decided that it's somewhat fuzzy but peanut shaped, and so identifies them as a pair of stars. A pair of stars can be further split into more pairs if necessary. On the left, we don't see that. On the right panel, for example, over here, some of those came from that process. The blues are things that are that it said, well, I find something here, but I don't have enough signal to noise to make the distinction between whether it's a single object or if it or to parse its shape. There's the occasional thing that is yellow, and that says this is fuzzy and not peanutty, so it's probably a galaxy. Now, large galaxies are not going to be fit this way. Things that are in the box that it's in the that has a fuzzy shape will be found this way. But when we're really interested in stars, so if you have a large thing, it'll ride over that because the background is allowed to be variable. And what we do is fit the PSF to the background, fit the background with the PSF, so it doesn't suffer from that. So here's a rendering of the histogram as a function of magnitude, where the red are the bona fide stars, the blue peak at the very faint end are things that didn't have enough signal to noise, and sometimes there are pathological situations where that comes into play even brighter. The greens are few, but there they are, and there's a faint trace of yellows here, if you can see that. This is for the that was for the Fornax image, and this is for the 47 tuck image. So it's telling you that it's doing basically sensible things. You're getting back expected kind of classification and the kinds of numbers and things that are reasonable. So here are the color magnitude diagrams that we get, and these are working on the single visit images, but all of them taken together, making a union set. And here is the 47 tuck halo plus SNC halo field. And you've seen these before. So here, if your eyes are sharp, you see that on the bright and the red side, there's a fuzz of objects consistent with them being binaries, but on the other hand, anything that's not resolved will show up over there. So it's a combination of unresolved things and or binaries. If you go to a deep image, you go a magnitude deeper. This is in a different band, so it's not directly comparable, but it goes past 24th on the outside, and the more crowded regions, well, this is really a color cutoff, so that doesn't make sense. So now there was. So I'll end with some thoughts, and that is that the sensitivity to the background determination, it really affects the fitting versus. I mean, we do it by fitting to it, and we think it's better for writing over local fluctuations and other things instead of doing it by direct determination that some of our competing code does. Complex background structures in crowded fields are dealt with. It affects the sensitivity to background also affects how you get the aperture magnitudes of things at the end, because if you've got your background not quite right, then your aperture corrections will come out the wrong way. I won't go through the rest of these points in the interest of trying to keep time for discussion. Accurate subtraction of brighter features. So Dupont works basically by fitting the bright things first and then dropping the direction threshold and fitting the next layer of things. So in the final run, you've got everything subtracted out, and you take one star at a time, put it back on what is a blank background with everything else subtracted and refit it. So that is what the final thing comes up with. Being able to subtract the right PSF is important to getting the right background and identifying all the neighbors and not tripping on residuals of badly fitted stars. So this iterative approach, as opposed to trying to fit groups of stars together, is both efficient and fast compared to simultaneously trying to fit everything. So one point I wanted to make is that in order to do this, it actually, for the deep images in particular, it would be good to propagate the background subtractions all the way through, because whatever algorithm has been adopted is then lost in the final deep image. And if you can't access it, I mean, so you have to subtract it in order to work but you can do the same work on what you've taken out and keep it as an extra plane in the and that would help in the long run. But that's I won't belabor the point. I'm done.
Okay. Do we have questions? Oh, fantastic.
It's very interesting, Abhi. Can you go back to about your third or fourth slide? You had some words there about galaxies and other pathologies. Are you just trying to get a rise out of us extragalactic people? Okay. Yeah, because you can't seriously be worried about extragalactic contamination given the extinction of the galactic plane, are you? Or are you actually worried about that?
Oh, why, man?
In I-band, perhaps. Yeah.
Why? Well, you know, the background galaxies
Why?
don't go
Why
away.
band?
They don't.
Right, and they're there. And if you're trying to do stellar photometry, then
Yeah, you still have to map them out and stuff. But,
Yes,
but yeah, that's kind of what you're saying.
Right, that's
Okay,
what I'm saying.
fair enough. Fair enough.
yes, I was trying to get a rise.
Yeah, this is a great presentation. Actually, Zilko's student is working on trying to incorporate.
Audrey,
Yeah, that's right.
Yeah.
Yeah, so okay, I think it'd be
we were in
also
touch, but
Christian
we sort of
Johnson.
lost connection, and then so if she's here, I'd be happy to meet her. If you,
I think it would be great to kind of do a runoff, have like a group of fields that these different methods are applied to, just to make sure that whatever is finally incorporated into
we
the
did
pipeline.
that with Massimo's thing, and they're very comparable. Yeah, ours takes half the time.
Yeah, okay. Well, talk to Zelko, maybe it'd be better to incorporate your into the actual pipeline.
Do we have questions online?
Oh, sorry.
Your last slide said it was fast. What is fast in this context?
So the 47 tuck image, the one in the central field, takes in the default part of it takes about 2 minutes and change on my on a single CPU on my desktop, my office. The whole front end and back end stuff, which is not efficient at the moment, adds another couple of minutes. So if you were to run all the 9 chips of ComCam, for example, in parallel, you know, you could get the whole image done in 5 or 6 minutes. There's room for improvement, but that's where we are. But the guts of it, the default part is only 2 minutes.
How would that compare with the DAO folks case?
About a factor of 2 from what Massimo tells me. But they were running on a cluster, and I don't know what the we should be doing better. We should be doing better yet compared to them. But
I have the impression that this can get much faster than the OFOG solutions.
yeah, but we're at the moment limited by the front end and back end, which we're running still in IDL, and that's not sufficient code to run it in. Right.
Do we have questions online? Okay, then maybe people need time to digest, and we can continue this on Slack. And yes, or not? Yeah, and next is Sage.
Oh,
No.
Okay.
Oh, that's pretty good. Okay. Hello, everyone. My name is Sage. I am a new grad at the University of California, Berkeley. I'm going to be presenting on the simulation of microlensing events for Rubin. As you heard from Natasha, microlensing events occur when a source passes behind the lens. I'm not going to go too much into details because I think Natasha did a great job at that. But something I want to describe more in depth is that we categorize microlensing events based on the source and the lens. So things like binary sources and binary lenses will affect the microlensing shape very differently.
So microlensing light curves are generated using the popsicle pipeline. The pipeline consists of Galaxia, which gives us a galactic model in UBV. We then transform that UBV photometry into Rubin photometry. And then within that galactic model, we inject compact objects. This is black holes, white dwarfs, neutron stars. And these are generated with SPICY, which uses mist and accounts for atmospheres. We then plug that galactic model and compact object system into Popsicle. Popsicle will then allow for the events to run over time and simulate the microlensing events. And we output those parameters into light curve links, which then simulates the light curves with the correct Rubin cadence and noise. So this is, sorry, to get a little bit more into how we actually do the transformation. This is something that we had to do on our end. What we do is we take many spicy isochrones of different age and metallicities, and we plug them into a grid of color for UBV and extract the Rubin data from also generated spicy isochrones of the same age and metallicities. And then we do a linear interpolation between the points, and then a nearest interpolation for anything outside the isochrone that doesn't get captured. This is only valid for zero extinction, which is the only drawback, but is very powerful for our case. Okay, so the microlensing simulations are finished up until the light curve links step. Here's a map of what the microlensing simulations are made for. So each of the red patches is a different popsicle simulation where we've generated microlensing events for that specific patch. The size of the patch determines kind of how many stars that it basically tells you how dense the stars are in that area. So because of compute time, we obviously can't just generate as many stars as we want. So we have smaller and smaller patches as we get closer and closer to the bulge. The color of this plot represents the event density. So here we're looking at the number of microlensing events per star per year. What we'd like to do with this is we'd like to say, what is the actual microlensing events per year? But obviously we can't do this until we know what the actual star count from Rubin is. So in the meantime, what we're planning to do is we're planning to use a decaps as a Rubin-like and basically multiply it along the galactic plane to then get a event density per year. This will give us a better idea of what we can expect for the microlensing distribution across the galaxy. This is also only for negative value. Yeah, so what are these microlensing events what do these microlensing events look like? Well, we have great photometry for all 6 bands along with errors. We also have all the microlensing parameter statistics. So we can see for as we get closer and closer to the bulge, we get smaller and smaller TE. If you remember from Natasha's talk, TE corresponds to to the mass to the square root. So in the bulge, we have a higher probability to get like smaller mass lenses. And then as we go further and further out, it's more likely that your microlensing event is due to a higher and higher mass. Some event type statistics that are within our catalog is going to it can be shown here. So PSPL means point source, point lens, whereas BS or BL mean binary source and binary lens. And as we can see, the number of binary source, binary lenses is increasing as we get closer and closer towards the center, whereas the number of point source binary lenses gets increases as we get further and further away. This is to say that our models are sensitive to the initial inputs of the binarity along the galaxy. So it is highly susceptible to changes in our galactic model. Something else we can look at is the lens type distribution. So as we get further and further away from the galactic plane, our models show that the neutron star population for microlensing events is significantly increased. This is to say that our light curves in our simulations hold the initial mass function across the galaxy, and the velocities, and those can be extracted out from our light curves, and it's just something interesting to look at. Okay, so finally, our light curves are intended to be used for public use. We want to make these accessible to all, but these are not accessible yet, unfortunately. Some of the benefits for these simulations is that we have proper color blending between nearby stars. So this is really great if you're trying to account for especially the crowded fields. The other thing is that we have the actual properties of the lenses and sources for each microlensing event, and these will also be made available. Some of the future work that I intend to do is I want to fit the microlensing light curves with a PSPL model. This is so that we can better constrain whether the microlensing event is actually detectable based on the cadence and the noise of the data. One of the issues with this currently is that while it is great that we do have multiband imaging, it means that the fitter has to do a lot more work in trying to get it or converge at a solution. So there's a lot of issues with compute time. But yeah, I'll take any questions.
I have a question as a chair, or two. Do we have time for two? Okay. First of all, how do you plan to? Which channel will you use to make the light curves public?
We're not sure yet.
All right. Okay. Cool. I would suggest Zenodo or a thing like that, but there might be better ways. Another thing that I'm also interested in is the underlying model. It would be really cool to, well, maybe, upon request to have the access to the underlying popsicle simulations, because I think we as a community might also want to use that too for multiple reasons.
Yeah.
All right, then maybe if people have questions, we can move to Slack, and the next person is me.
All right, hello everyone. I'm the last talk of the session. My name is Katarzyna Kruszyńska. I'm a postdoc at Los Cumbres Observatory working with Rachel Street, but I will be soon moving to Carnegie Mellon University in Pittsburgh. Today I would like to talk about a Python package that I have been working on for a while now. And finally, it's at the stage that I can share with the humanity. So it's called Microlensing Proud, and it's a scalable microlensing event modeling pipeline. So why I decided to build this pipeline, with other people, it is because with microlensing we have 4 problems. First one, and that's Natasha and Sage, well, Natasha mostly has already signaled, is the inheritance degeneracies between the microlensing model. You can get the same kind of light curve, which I've shown in this image here, with different parameters, and maybe if you have more data, you can constrain it better, but not always. So for example, in this case, I found like 3 types of models based on the data that I had. And like with the better data, I found 2 and I couldn't distinguish between either of them. The second problem, that it's the computational expensive modeling. So basically in microlensing, we want to fit different types of models and find the best fitting parameters for those. And it takes time, especially maybe for like the simplest models where we have only single lens and single source, maybe that can be like relatively fast. But when we move to binary lenses, it becomes very expensive, and it can take from hours to days. The third problem is each team has a different approach. They prefer different methods. They have different approach to modeling which type of models they approach first, what type of packages they use, what type of software, or even like what type of how they define their parameters. So that's a thing. And the fourth problem is in the current modern day surveys, the event rate gets really high and unsustainable for our current approaches. For classical surveys, we get up to 3,000 events per year. These are like the classical surveys that look at the galactic bulge with one maybe 2 meter telescopes. With Rubin LSST, we can get even up to 10,000 events per year, depending on the cadence and the capabilities of Rubin that we don't exactly know yet. This is a slide with history that you can look at, but I would like to point 2 things. So we have modeling packages and we have modeling pipelines. Most of the modeling done by the microlensing community is done with proprietary software, which is not publicly available, with adaptive contouring released in 2007 by Mark and Dominic being like the difference. This has changed in 2015 with BBB binary lensing, which is a code that allows people to build magnification maps, especially for binary lenses quickly. And in 2017, the first publicly available modeling package, Tylema, was published, and since then, like things have been changing. However, there's still a lot of proprietary software. However, right now the field has completely changed. There is one notable example called RT Model. It actually was being developed since the mid 2010s. It's the first modeling pipeline that allows autonomous event analysis. So you just give you give an event to RT Model, you set it up, it runs, and it spews out the best fitting model with a wide range of options, including binary lensing. For modeling pipelines, most pipelines are not publicly available, and they are fine-tuned towards specific needs of surveys or catalogs. There are like 2 notable examples in here. Artemis is an old system that has been built since 2007-ish to efficiently follow on exoplanets, microlensing events that have exoplanet signatures, and it has actually spawned the microlensing and RT model. Another example is MSOS, which is a pipeline built for the upcoming Roman mission. So knowing that, we have identified 4 drivers to build the microlensing cloud package. First of all, it has to handle event rates of Rubin LSST or Roman Galactic Bulge Time Domain Survey. They will deliver thousands of events, so we have to do this efficiently, which is the second thing. We have to fit, for community purposes, we will have to fit hundreds or even thousands of events every day to figure out which events are the most important. Third thing is the flexibility. The pipeline has to be able to accept different types of packages that people prefer, has to be used for different purposes. And also it has to run in different types of environments, including cloud or computer. And finally, it has to be self-contained. It has to provide as much data and information as possible to the user without their intervention, so they can make a final decision at some point later. This is a very rough image of the microlensing crowd architecture. It has like two main modules, which is the controller. The controller handles basically gets information on how much computing processing power it has, and then like puts the events into queue. It knows where to look for them, and then it also knows where to like save the data. Then there's an event analyst. So for each event, you assign an event analyst. Each event analyst can be configured completely separated from another event analyst. So you can add different features there, and even like set it up completely differently. So like, for example, if you know that your like one type of event will have like a very noisy light curve, you can set up your for example, your outlier removal differently than the other event. Event analyst has 3 sub-analysts. All of them are optional. I mean, obviously, like the idea behind the package is to use the fit analyst, but you can even run it without the fit analyst if you want to. There is the light curve analyst, which is doing basically like cleaning up your light curve before event modeling, removing like invalid entries, or doing outlier removal. There is the fit analyst, which is handling like the modeling procedure, going for like different stages, and it also right now has a very simple anomaly finding procedure, which flags to the user and the pipeline whether or not we think the event has more than one lens. And finally, there's the CMD analyst, which based on the results from the fit analyst can produce a color magnitude diagram for a selected catalog, which will provide more information about the event. So these are the available features that I just talked about quickly. There's a little bit more. Currently, Microlensing Pro supports only the Pilema fitting package. However, it can be expanded to support anything you want. And this is the QR code to the repository. And I will just go into future plans. It is the same QR code, don't worry. If in the future, in the nearest future, I want to implement like the simplest way of fitting binary lenses. Another step is to provide all of the like integration functions to make it run on the Galactic Science OPM that Natasha has also mentioned. And then if there is time at some point, I would also like to use different anomaly finding techniques for reasons that I can talk about later. And that's it. Sorry.
This sounds really cool, but who's Ralph?
Oh, Ralph, well, the package is named after my friend who has passed away last year. Yeah, it was a good choice, like because I was thinking about calling it after my cat, but then I would get angry at my cat or the pipeline. So yeah.
Well, it's a fitting tribute. It's a good name. Yeah. Can you tell us some of your other anomaly finding techniques?
Yes. So first of all, let me show an example. Right now, what I have is very simple. It's a technique that's used for outlier removal. I don't know. I found it out with AI, and then I went from there. It was great. So when I was playing with the outlier removal, I noticed that like it can also it's basically calculating the median average deviation on like windows, and the user specifies the length of the window. And if you play around with the length of the window, you can pick up features that are like if you set like a short window, like let's say 1 day, it will be mostly sensitive to outliers. But if you set like the window to something like that is slightly longer than your expected anomaly. So for example, in terms of for exoplanets, we accept for, let's say days, then it can like also kind of like start flagging the sharp features from that. I tested it with Roman data and it works relatively well. It's super simple and easy. However, then I run Microlensing Pro on, and I apologize for the plot. I run it on 100 selected simulated events from LSST. This one was one of the best samples events in here. Different dot means different color. This was the best fitting model with a point lens point source. Oh, yes, that's a simulated LSST event. And there's like this little feature in here. You can also see it in residuals in here if you can follow my cursor. So this corresponds to this little thing in here. However, because I'm using the median average deviation and like medians and everything in Windows, this feature is too sparsely sampled, and like the median average deviation follows this too well. So another technique that I want to implement is the technique that was developed for the Artemis system, which is called Signalman. It's basically a test of a series of like simple statistical tests that check like if the points follow in the same direction. Like there are like different little tests that like check the scatter, and they also like it can go across different filters and different observatories. So like each point is looked at in sequence, and for this filter I just do it per band, which is also not very efficient. But there are also other things on the market. For example, there are anomaly finders developed for the Roman galactic Botch time domain survey, and I also plan to test that at some point in the future.
Yeah, thanks. So I suppose for LSST, a good use of this package would be one to help identify if an event really is a microlens, and if there are a range of models that fit a possible event that diverge in their predictions, that you could then schedule follow-up observations with other telescopes to try to pin it down. Right?
Yeah, that's exactly the original use case.
Yeah.
That's why I want to implement it into Galactical PM. Basically, Galactical PM will handle the modeling and spew out some priorities based on the models that they get and like other statistics. And then we will grab that information from them and then follow up and then send our data there and like run this in a loop.
Given the statistics of the number of events that you expect and how much observing time you would need to discriminate, do you have an idea of the number or the fraction of microlensing events that you could pin down in this way?
I have to look at towards Natasha, but we expect that okay, I can say that. So in microlensing, roughly, we expect that 10% of events are caused by binary lens events, and then 10% of that is by exoplanets. So with Rubin, we will end up with 100 planetary events and then 1,000 binary events. So obviously, there is a bottleneck. We hope, especially if we have a robust anomaly finder implemented, we hope that will make things more efficient. However, the pipeline, I didn't mention it. There's like a lot of things that I had to like skip over, but the pipeline is split into two modes. There's an ongoing event mode and a finished event mode. I do not plan to do binary lens modeling before the event is finished. Just because when the event is evolving, the binary lens model is very, it's very wonky. Also, it's expensive. Like, you know, in a good case, it can take an hour. In a bad case, it can take half a day at least. So I want to avoid that. I just signal. Okay, I think there's something weird going on. This is like diverging from a single lens, single source model. Community, do something with this.
Thank you for all this. And I'm curious, so one of the applications is on the Rubin alerts. I don't think we've seen exactly these events yet, but have you tried running on a sample alert history from maybe one of the brokers or so just to test whether that infrastructure works yet?
No, not yet. I only tested it on my computer. It's relatively efficient. Even though I have like a relatively powerful computer that I tested it on, but like it took for 100 events with all bands and all photometry, it took 40 minutes to run. So I'm pretty optimistic. That being said, there was also a lot of garbage in there. Like there were events that didn't have any point during the actual event. So I didn't do that type of selection on the simulated event. Yeah, there's more testing.
No, I think it'd be interesting to do the testing with real data, even if there is no actual event there, just to see, do that integration test.
Yeah. One thing that can be done with it is to like run only like a specific category of an event, and I think that for like quick event alert identification, that can be also useful. Like it's very flexible. Like basically you can like turn every knob everywhere as you like, provided that your YAML, your like configuration file, which can be either YAML or JSON, is going to get longer and longer. Yeah.
Any last questions or questions online? Okay, let's give another round of applause.
Oh yeah. Now we have time for discussion.
Well, I guess there's only a couple of minutes left.
Oh.
But if anybody had any other thoughts, yeah.
Thank you all for indulging me. As you heard before, I'm an extragalactic guy, so this local microlens is a completely new me. But I really wanted to come to this session because I was trying to learn things. So if you guys, especially all of you who spoke, could address this point, for me, they're expected, as you said, every year about 100 planetary events, about 1,000 binary events, and about 10,000 events overall. Right? If each one of those were spent, say, an hour to compute, that's still fewer hours than a full year, right? 365 times 24 is greater than 10,000, or thereabouts. It's about 10,000. And with lots of other people running them, right? It's not going to be just you guys doing it. Shouldn't there be plenty of compute to analyze all of these things effectively sooner or later and have enough comparisons so that you'll get it right? I mean, is that right? Is there a need to go for ever more efficient and ever faster algorithms that might skip a few steps and therefore lose information as a result?
Well, I think you're on the right track. I think a lot of this will be like different science groups will have their different like favorites, and like one group would like to look at. Also, there's another problem. I did not even tackle the detectability of those planetary events and binary lens events with Rubin and sparse cadence. Like we expect that, but with the we have not run any like checks on how does our current simulation affect the current options that affect planetary or binary lens events detectability.
So will those take longer then? Will those take longer then?
The question was, will those take longer then? I think in principle, like, the less constrained you are, potentially it can take longer to explore the potential parameter space. And a lot of the times when these are becoming more efficient, it's not by skipping steps, but rather like, especially for binary lens modeling, there's actually like a fifth order polynomial root being solved. And so it's like finding more efficient like root solving algorithms that aren't necessarily making it like cutting corners, but actually making it more robust and better. I think also, while we had you all here, we also wanted to ask if there are other like crowded field alert like filters that are going into these brokers that like we would like to connect, and like since we're all microlensers who organize this session, but there's a lot of crowded field science we want to like connect as a community.
Yeah, one thing that we can advertise maybe a little bit, hold on, I don't know how much time we have, but the Galactic OPM is basically caters not only to microlensing, but if someone brings their own different galactic plane science and wants to use the system and like provides metrics and like some other techniques, it can be implemented into there and like make your interesting cases detection more easy. So please, terrorize the galactical PM. I will post the link, and I think Marcus will kill me. I will post the link to the chat, the Slack chat.
Well, thank you all for coming. Have a nice rest of your day.
Thank you so much.